This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. At the CERN laboratory near Geneva, the Antihydrogen Laser Physics Apparatus, or ALPHA experiment, is an international collaboration working with the antimatter counterpart of the simplest atom, hydrogen. Since 2018, the team has been running an experiment called ALPHA-G, seeking to understand gravity's impact on antihydrogen. We are joined by two senior researchers from the ALPHA experiment, Professors Joel Fajans and Jonathan Wurtele, who run the Fajans-Wurtele Plasma and Antihydrogen Physics Research Group at the University of California, Berkeley, to hear about their latest results. Thank you both for joining us today. What results are you sharing with us?
We're going to be talking today about the first direct measurement of the influence of gravity on antimatter. Now, most people, if they've heard of antimatter at all, heard of it in some sort of science fiction-y context. But it really exists. It's a form of mirror matter, which is very uncommon, and we'll discuss this a bit more, very uncommon on Earth. But since it was first postulated and then discovered about 100 years ago, scientists have speculated about how it would interact with gravity. Would it fall downwards like everything else, or might it just maybe, very unlikely, but just maybe, would it have fallen upwards?
How does antimatter behave in gravity?
Well, all the indirect evidence is that it behaves exactly the same as matter. The theory of general relativity says it should behave exactly the same as matter. But until the result today, nobody had actually done a observation that could, for example, rule out antihydrogen moving upwards as opposed to downwards in a gravitational field. So broadly speaking, we're making antimatter, and we're doing a leaning tower of Pisa kind of experiment. We're letting it go, and we're seeing if it goes up or down.
Dr. Wurtele, can you start with what is antimatter?
So antimatter is an interesting history. In the beginning of the 20th century, there was special relativity by Einstein, and then a decade later or so, general relativity, and then a few years later in the early 20s, the development of quantum mechanics. So 3 revolutions in physics over a period of 2 decades. But there was no connection between the quantum mechanics and the special relativity initially. Dirac, by the end of the 1920s and in 1930, he published a paper in which he had connected special relativity to quantum mechanics. And so he had a theory, for example, of the electron, which is consistent with both quantum mechanics and special relativity. But his theory was an equation, and his equation actually admitted a solution which had a positively charged electron as a possible particle. And this was a particle that he basically found in an equation. And he said in his paper, if it's in the mathematics, maybe nature gave it a shot. So you have to understand this is a revolutionary concept. You derive an equation, you see a particle coming out of it. And 2 years later, Anderson, working at Caltech, sending balloons up to study cosmic rays, found a track, the remnants of a particle, which was the mass of an electron, but it was moving as if it had a positive charge. And that is the anti-electron, or the positron. So it took only 2 years between Dirac's prediction and the discovery. One of the big problems we have is that matter and antimatter are incompatible. As everybody knows, if you take matter and antimatter, take a positron and electron, knock them together, you get out 2 gamma rays, which would be X-rays with 10 times the energy. So E equals mc squared, you get energy out. There's a question then, if the laws of physics actually say that antimatter and matter should be produced in roughly the same amounts, yet here we are, there's almost no antimatter, luckily for us, we're not destructing on it. And that's one of the great problems in physics, called the baryogenesis problem. Why is there preponderance of matter over antimatter? And that's one of the things that the ALPHA experiment is trying to look at.
So you talked a little bit about the particles annihilating when they come in contact with anything. Why else is it difficult to study antimatter?
It's difficult because it annihilates. As soon as it touches something, it annihilates. And therefore, we have to be very careful as we manipulate it. So we have to put it, it's made at CERN at the antiproton decelerator. And the antiproton decelerator is a specially made device. We create the antiprotons by hitting protons on a dense target. The antiprotons are created almost at the speed of light. They're decelerated, and then they are given to us. We then take them and further decelerate them. And all the time with all these manipulations we have to be very sure that they can never touch any of the walls, because as soon as they do that, they're destroyed. So we're manipulating them with electric fields and magnetic fields. And the final experiment is done in what's called a magnetic bottle or magnetic trap, which is basically a magnetic field which then confines the antihydrogen.
So, Dr. Fajans, he just mentioned kind of how these things are being made at CERN. Can you go through it a little better, how it's made, how you're capturing it and storing the antimatter?
Sure. It's a complicated process, and it's taken us quite a long time to become at all efficient at doing this. But the first thing that we do is we take the positrons and antiprotons from CERN, and we make plasmas out of them. So where do we get these particles? The antiprotons are delivered to us from CERN, as Jonathan just mentioned. The positrons, however, come from radioactive sources. Now, there are no real sources of static sources of antimatter on Earth because they would just annihilate. But there are radioactive materials, some of them natural, that emit positrons. For instance, one of them is potassium-40. And there's a small amount of potassium-40 in a banana. So when you eat a banana, inside of your body, you'll make positrons. It turns out for the amount of potassium that you get from eating one banana, you'll wind up with about 100 positrons being made inside of you. A somewhat scary process, but that's part of the natural background radiation that we all experience from cosmic rays and from uranium in the soil and things of that nature. In any case, we take these positrons on one side and the antiprotons on another side and make them into plasmas. Now, what's a plasma? Plasma is the fourth state of matter in an energy continuum. So the coldest things are solids. Then if you heat them a little bit, you get liquids. And if you heat them further, you'll get a gas. And what many people don't know is that if you heat the gas even more, you'll get a state of matter called a plasma. Now, it turns out that plasmas are incredibly common. They make up over 999% of the matter in the universe. Everybody's taught in elementary school incorrectly. The sun is a gas. It's not. It's a plasma. So plasmas are really common, but they're not typically found on Earth. Our plasmas are actually quite unusual because they're what are called non-neutral plasmas. Most plasmas have equal amounts of positive charges and negative charges. Our plasmas, though, since we keep these constituents separate, they're only antiprotons, positive charges, and only positrons, negative charges. And you might at first think that that would cause them just to blow up and it would be harder to confine. It's actually easier to confine these plasmas. So we can confine these plasmas essentially forever. Whereas if you have a normal neutral plasma, you have to spend absurd amounts of money to be able to confine them even for a few hundred seconds. And we can manipulate them very well because they're charged unusually well. We can hold them in what's called a Penning-Momberg trap. Now that uses electric and magnetic fields to confine the charged particles. And we do a lot of manipulations on those particles. In a typical experimental cycle, for instance, a great deal, maybe the vast majority, unless we're doing laser spectroscopy, the vast majority of the time is spent doing plasma manipulations to get these plasmas into the shape and temperature that we really need them to be. We need them to be shaped like a needle, actually sort of like the dimensions of an actual physical needle. But the harder thing to do is that we have to get them very, very cold. Contrary to what I earlier said is that plasmas are hot, these plasmas are cold. We have to get them down to about 10 Kelvin. And that's really, really hard. We didn't know how to do this when we started out. We've learned gradually over the years how to do it better and better. But it's certainly the most difficult step in the synthesis of antihydrogen is to make them sufficiently cold. Now, once we're satisfied with the properties of the plasmas, we've got these two plasmas, antiproton and positron plasmas, next to each other. And crudely speaking, what we do is we electrostatically kind of tilt them into each other so that they overlap. In the second or so that they do last in this configuration, they're going to make antihydrogen atoms through a process through three-body recombination.
How did you actually carry out the experiment with the AlphaG device?
The first thing we had to do was to change all of our thinking, because every trap that we'd built up to this point was a horizontal trap. And if you're trying to study gravity, obviously you want a vertical trap, something aligned with what you think is going to be the direction of gravity. Turns out to be the direction of gravity. And this sounds simple enough. You just take your trap. No, it's not simple at all. Among other things, the particles are still coming in from the CERN complex horizontally. So the first thing we had to learn to do is to make them go around a 90-degree bend. That was a really hard problem, which was actually solved very, very nicely by a graduate student. So now what's the next problem? The next problem is that even though they're very cold, they're not actually that cold. And they're moving pretty fast. So one way you could imagine that you would measure the effect of gravity is that you could just let them go upwards like in a water fountain. And eventually they'd reach some maximum height and they turn around, and the turnaround point is set by gravity. It's like throwing a baseball upwards. No matter how fast you throw it, eventually it's going to reach some place and then it's going to come back down. It turns out that our particles are, even though they're half a Kelvin, they're still moving so fast that they would go hundreds of meters high into the air. We use the fact that the antihydrogen atoms are repelled by strong magnetic fields. That is the whole basis of our trapping. So what we do is we have a lower coil down here and an upper coil up here. And we're very, very careful to make sure that they have exactly the same field. And initially, our atoms are trapped somewhere in between. They're trapped something like this, and they go up and down and up and down. And they'll do that forever, really. And then if we slowly lower the field, so we have these two strong magnets, and we slowly make them smaller and smaller, lower and lower fields, what will happen to the orbits is now they'll be able to get up the side of the bathtub, up the hill, further and further. So they started out doing something like this, and eventually their orbits will get extended and extended until they're just about making it out of that bathtub, but not quite. And then if we lower the field still further, then they'll be able to go out of the bathtub. They'll fall out. Now, if they escape up and they'll hit something up there because they're no longer confined once they get out of our bathtub, and they'll annihilate. And that makes a signal that we can see. Likewise, if they were going down at the moment that they can escape, they'll escape, get out of our trap, they'll on the trap, hit the wall, annihilate, and we can count that. We can see how many went up and how many went down. And that's going to be the basis of our experiment, except that I left out one part, gravity. So what does gravity do? Well, assuming, as it turns out, that gravity makes the antihydrogen fall downwards, what that means is we started out with these magnetic fields, which are strong. But gravity adds this downward force, which makes the field at the bottom just slightly weaker, ever so slightly weaker. And that means an antihydrogen atom, as we slowly lower these fields, it takes these bigger and bigger orbits, but it's always going to go microscopically further downwards, further up the hill of the magnets on the bottom side than on the top. And that means that a preponderance, it's not going to be all of them because it's a statistical problem, but a preponderance of them are going to fall downwards. We can count that. And that's the essence of our experiment. We counted the ones that fell out of our trap on the bottom and compared them to the ones that fell out on the trap on the top. More of them fell out on the trap on the bottom, and that's how we know that gravity acts for them to go downwards.
So, Dr. Wurtele, how long did the AlphaG experiment take to come together and carry out?
So it took about a decade. The genesis was that in our very first experiments on antihydrogen, we would, you make antihydrogen, but you don't know how many you've made. You're combining antiprotons and positrons. The only way you know what you made is by, you make a trap, you combine, and then at some point you have to turn your trap off and you see what hits the wall. So Joel and I began to think about what actually happens as you, in his analogy with the bathtub, you lower the size of the bathtub. Gravity would have some influence on that. And maybe, for example, you would see more antihydrogen, even in a horizontal trap, more of them coming out towards the bottom than the top. And so we did a retrospective data analysis and was a very crude estimate with which came out about a factor of 100 times gravity for up or down. So it was about 100 G. And we've improved that maybe now by a factor of 300 in this experiment to compare. But in the initial experiment, we couldn't rule it up or down. We couldn't say one way or another. What we realized by doing this analysis was that understanding the orbits, understanding how these antihydrogens move in 3 dimensions is really important. And of course, we have the vertical trap. And it's the fact that in the leaning tower of Pisa, you imagine just dropping an antihydrogen, it goes up or it goes down. But in the real world, these things are not made just with vertical velocities, they're made with horizontal velocities. And you have to worry about the full configuration of this trap. And that actually took a lot of worry and a lot of effort of the collaboration. But basically, it was 10 years to put it together.
So speaking of the collaboration, there's a lot of kind of international and cross-agency support involved. Can you tell us a little bit about some of the partners?
Yeah, so ALPHA is a wonderful collaboration. There's about 50 people. We have institutions from all over the world, and without this sort of collaborative effort, which involves detector experts, atomic physics experts, laser physics experts, plasma physics experts, without the huge team, we couldn't have done this at all. There's a team of postdocs from all these institutions, the graduate students from these institutions, working 24/7 at CERN, along with local senior scientists at CERN. So it's a big effort to make this thing work. The funding agencies, of course, NSF and DOE have been very generous with us for, I guess, almost 18 years now. They've, when some people thought there was no hope for ever doing anything, they supported us and supported us and supported us. And I think that's a real testament, again, to sort of a long-term visions for research.
I'm going to jump in here. I was convinced in 2008 that this experiment would never work.
What changed your mind?
Well, it started to work.
It took really 5 years to trap the first antihydrogen, and then it was the first season we were arguing over in 2010 did we trap 1, 2, 3, 40.
Actually, it's worse. In the beginning, we gave them names: Jonathan, Mary, the ones that we thought we had trapped.
But then, advances, and I should say, since we're plasma physicists, a lot of the plasma manipulation techniques were absolutely essential to increasing our trapping number from just a few every time we tried, or 0.1 even when we started out every time we tried, to many every time we tried. So plasma physics was essential to the success of this experiment. Without the advances in plasma physics and understanding how to control non-neutral plasmas, how to combine non-neutral plasmas, how to use non-neutral plasmas to measure magnetic fields, this experiment couldn't have been done. And the NSF support over the years was absolutely essential to getting that done, and DOE support, both of them.
Dr. Fajans, there's a couple lectures online where you kind of talk about this in a fun way. So I wanted to ask you, what could large quantities of antimatter be used for?
You had to ask. So online, people are very interested in antimatter, and you can find all sorts of things online. And some of them might even be true. One of the things that you can find online is that antihydrogen is the most expensive material that's made by mankind. Somebody put a price tag that it's $50 trillion per gram. And making a gram would take thousands of years. Alpha has produced something like, and don't hold me to this number, but something like 10 to the minus 16 grams of antimatter. That's 0.00000000000000001 grams. It's not very much matter at all. And in some ways, this is too bad, because if you had a fistful of antimatter, you could probably make a spacecraft which would go all the way to the stars. Why is this? Because antimatter and matter to put together is the densest form of energy release that we know. And an annihilation of antimatter has about 10 to the 10th times as much energy as an explosion of an equivalent amount of TNT. And sure, you could go to the stars with it, but on the other hand, you could build a bomb with that sort of thing. And that's been speculated about in the movie Angels and Demons, for instance, if you had the misfortune to read that book or see that movie. Or in also in Star Trek, there were antiproton torpedoes, if I remember correctly. The thing is, it's just utterly impractical. For better or worse, we're never going to go to the stars this way unless you could come up with some way that grabs the fuel through giant magnetic fields and you can see all sorts of things in science fiction. We're never going to build a bomb a spacecraft or a bomb that's powered by antimatter. On the other hand, you can do practical things with antimatter with much less of it. And one of the practical things that people use antimatter for is PET scans, positron emission tomography scans. As you probably know, those are used to detect cancer and delineate boundaries of cancers. And it's a very important technique in medicine. That uses more antimatter than perhaps we use, but still significantly, not even close to the sort of gram level that people in science fiction talk about.
I feel like there's so many more areas we could dig in today, but I want to ask you one final question. And it's a little broader, but how does understanding antimatter impact human knowledge of physics?
Well, there's a lot of we don't know, and the baryogenesis problem I already mentioned. If we could find through studies of antimatter why it is that this is preponderance of matter over antimatter, I think there'd be a huge advance in our understanding of physics. If we find a difference in the way in which antimatter behaves compared to matter. So if antihydrogen were somehow different from hydrogen, that would be sort of a revolutionary thing, because the physical laws, both in quantum mechanics and gravity, say the behavior should be the same. So any difference would break some very fundamental, called CPT, but a fundamental property of physical laws. And so we are extremely interested to see if we can break them. It's unlikely because these are pretty good symmetries, pretty good laws. However, one doesn't know until one does the experiment. And so we're going to try higher precision. We know how to do higher precision, although it's not easy, gravity measurements. And of course, we're doing alpha as a collaboration, as doing higher precision spectroscopy and looking at other properties of antihydrogen and comparing that to hydrogen.
Special thanks to Joel Fajans, Jonathan Wurtele, Slava Lukin, Jason Stoughton, and Adam Eggers. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.